This is a really helpful concept when we're looking at graphs. You can start with the basic function f of x and multiply a number in front of it. So what happens to the graph?
This is a sine function. We will talk about that if you take trig with me. It's a really great graph for us to see what happens if you multiply a number in front of it, though. It makes it really obvious. So this purple function is your basic sine function. What happens if I multiply by a 5 in front of it? The green is my basic sine function, and now when I multiply by 5, ooh, it made it a lot taller. What about if I do 9 or 2, 3? It keeps changing the height and pulling it bigger. All right, well, what happens if I multiply by a 1/2? Notice now that purple graph is a lot smaller than it was. 1/3, 1/8, it all makes it a lot smaller. What about negative numbers? If I made it a negative sign, it's kind of hard to tell what's happening. So let's use an x squared graph instead. This is x squared. What happens if I put a negative in front of it? That's a little bit easier to see. The negative flips the red graph upside down. If I make it a -2, if I make it a -3, -4, -1/2, it's still upside down.
You should have noticed that if a was a negative number, it flipped the graph upside down or reflected over the x-axis. If a was bigger than 1, it made the graph taller or a vertical stretch. And if a is between 0 and 1, it made the graph shorter or a vertical shrink. The number tells you if your graph is getting taller or shorter. The sign tells you if you're reflecting over the x-axis or staying as is. Okay, what happens if we add something to the end of our equation?
All right, we can stick with our x squared graph to see what's happening here. This is a basic x squared graph. What happens if I add 2 to it? Oh, it moved the graph up. What about 3, 4? All right, let's try some negative numbers. -2, -1, -5.
So when we added something, it made the graph move up. When we subtracted, it made the graph move down. What if we want to actually change our function? If we have a square root and we want to multiply something underneath?
All right, we're back to our sine function. What happens if I want to multiply something as part of my sine function? What if I wanted to put a 3 in here with the x? It squished that red graph way more in, compressed it like a spring. A 5, a 20 compresses it even more. All right, what about if I do fractions? 1/2, 1/5, 1/10. It looks like it's a straight line, but that's because I've stretched my spring out so far. Again, a negative is kind of hard to see, so let's use a square root graph. This is a basic square root graph. If I put a negative inside with my square root, it flips the graph backwards. As opposed to before we talked about the negative in front, it flipped it upside down.
Just like before, the negative did something different from the number. So the negative reflects over the y-axis or flips it backwards. This time, though, if we multiply by a number bigger than 1, it actually makes it smaller. That's called a horizontal shrink, or it squishes it in thinner. So times 5 would squish it in and make it 5 times thinner instead of 5 times bigger. It's a little backwards from what you expect. And any number between 0 and 1, if we multiply by 1/2, it makes the graph stretch out wider. Think of a spring, you pull it further apart. All right, well, what happens if we wanted to add something inside a square root or an absolute value or something.
We can stick with our square root graph to talk about adding and subtracting inside. So if I wanted to add 2, oh, it moves our graph backwards, -2. If I wanted to add 5, it moves it to -5. If I wanted to subtract 5, it moves it to the +5. Or subtract 1, it moves it to the +1.
Again, just like my b value, this is backwards from what you expect. You would think a positive sign would move it in the positive direction, but it actually moves it backwards to the left, and a negative moves it forwards and to the right. Some common parent functions that you will see are a squared graph, a cubed graph, a square root, a cubed root, 1 over x, that's a rational function, an absolute value of x. So the way these a, b, k, and h values would manifest themselves in these functions would be like this. Some of your questions are going to use these specific common parent functions, and other times it's going to use a generic f of x like we have up here, or it gives you a starting graph instead of you having to know these specific 6 parent function graphs. A way to help you memorize this in case you ever need to memorize it is the a and k value happen to the outside of the function and they're vertical transformations. It makes it taller or shorter or moves it up and down, whereas the b and the h are horizontal transformations and they actually happen to the function itself. Like in the square root, those were underneath and part of the square root, or underneath and part of the denominator. The b and h values are horizontal transformations. They change width and move it from left to right. These two are backwards from what you expect, whereas a and k are straightforward. Again, the negative sign for a and b is a separate transformation than the number. And a way for you to remember if you reflect over x or y, a comes before b in the alphabet, x comes before y, so I think to pair them up that way. All right, let's do some examples. Identify the parent function and transformations and then graph. So whenever you're trying to figure out the parent functions, either have these 6 functions memorized or just look at what are your basic symbols here. So in this first example, my basic symbols are the absolute value signs. So my parent function is the absolute value of x. All right, well, what else is going on? I have this negative here and this +2 here. Reminder, if you need this, I have a negative out here and a +2. So this negative is telling me to reflect over x because it is with the a value. And this +2 is telling me to move up 2 because it is a k value. If I was going to graph this, a basic absolute value graph looks like this, and I would reflect over x or flip it upside down and then move the origin up 2. And this would be what your graph looks like transformed. Next example. The basic symbols I see here are the parentheses. And why would I need parentheses unless I was multiplying something or there was an exponent? So that's your reminder. X cubed is my parent function. All right, what other things do we see going on here? We have a negative, a 4, and a -1. A negative, 4, and -1. So that negative is with the b, which means we reflect over the y-axis. The b value is 4. You think times 4 would make it a lot bigger, but remember b is backwards from what is expected. So b equal 4 means we have a horizontal shrink of 4. You can also say it's 4 times thinner. I like to use this word because it just makes more sense to be very straightforward, but math books usually use horizontal stretch and shrink, so to be consistent with them, I'll use that terminology. All right, well, what about this -1? Again, that's my k value, so that moves the graph down 1. This is a basic x cubed graph. If I reflect over the y-axis, I flip it over the y-axis, I have to make it 4 times thinner and then move my origin down 1. So this graph will look something like this. Last example of these types, my symbol here is this fraction bar, so that's a reminder that your parent function is a fraction. We have x in the denominator, and you always need to put something on top, specifically a 1 as a placeholder. Okay, what else do we have going on? We have this 4 on top, this +2, and this -1. The 4 on top is an a value that changes height, so that's a vertical stretch of 4. It makes it 4 times taller. If you'd rather use the words taller, that works. Otherwise, you have to say both vertical and stretch. The +2 is an h value that moves it left and right. Remember, h is backwards from what you expect. You think +2 is going to move us in the positive direction, but actually it moves us in the negative direction, to the left too. And once again, we have k value to move us down 1. All right, this one's going to be super hard to graph because of the vertical stretch, but I can at least show you the origin will move left 2 and down 1. And without me plotting specific points, it's going to be really hard to show the taller, but my graph will look something like this. Let's do a couple working in the opposite direction. I'll give you the graph and can you write the equation? Unless it is one of those 6 basic parent functions, you can just use a basic f of x. This is a square root graph though, so I do want you to use the square root graph. And you need to know what a basic square root graph looks like. A basic square root graph starts at the origin and curves up this way. When I do these, I will most likely not give you any stretches or shrinks. It'll just move left, right, and any reflections. So in this case, this graph just moved to the right 1. It's a square root graph. Right 1 would be adding or subtracting something underneath the square root. That's an h value. Right is in the positive direction, so -1 is how I would write it in my equation. Remember, h is backwards from what's expected. So from the origin to this new graph is in the positive direction, but you write -1. What about this one that's way crazy? Look at your parent functions. It's a U-shaped graph. That means it is an x-squared graph. I like to use these a lot because you should know what a quadratic graph looks like. All right, this is the basic graph. I moved my origin down here. That was right 3 and down 1. So my x squared was right 3 and down 1. But I also flipped the u upside down, which is a reflection over the x-axis. This is the x-axis versus y. And that would mean a negative in the front. So when you have to do these, it will just be left and right, up and down, and reflections. Last example for these types of problems, write an equation with the following transformations. My parent function is x cubed. You need to write one that is reflected over the x-axis and a vertical stretch of 8. Reminder, reflected over the x-axis means that it is a negative a value. Vertical stretch of 8 is also an a value. I don't have anything about b, h, or k, so I don't even have to list them. Technically, I don't need these parentheses, but it just helps me keep things clear that this is for sure an a and not a b value. Second example, parent function is 1 over x. We're going to shrink it horizontally by 2 and move it down 3. Reminder, Here would be how you'd write your transformations. So shrink horizontally is a b value, down 3 is a k value. When I give you these problems, you just have to use this number straightforward. You don't have to try and figure out if you need to make that a 1/2 or a 2 or anything like that. So straightforward. And down 3 is my k value. You do have to figure out your signs for down and for left and right. Normally I say you don't have to write an a or an h value if it doesn't exist, but because this parent function already has a 1 there for the a, make sure you also put a 1 over your fraction.